Okay, so what do we got here?
All right, so this is my attempt to follow up on the sort of puzzle or mystery that I brought up last time. So I'm going to try to, and I think visible on the screen right now is this picture from last time, which is supposed to remind us of how this puzzle works. So this is, this is all about Artin reciprocity theorem type stuff, splitting patterns. So I mean, these pictures, right? This picture is very graph papery, and it's supposed to really remind us of the Gaussian integers. And what we're sort of seeing on this picture is some colored pictures that represent something like congruence patterns on the Gaussian integers. And I'm trying to remind ourselves, especially myself, of how to interpret this and of what the puzzle is. So, well, right, and there's some helpful legend written down here. So it says that this is supposed to be a depiction of GL1 over the ring, the Gaussian integers mod 9. So I guess I'm using an underlined G as a symbol for the Gaussian integers here. Okay, and yeah, and so that's what this picture is, and it reminds us here that there's like this 72 elements in this group, which means in this square there's 81 elements, but there's only 72 elements in the group, so there must be those 9 zero divisors, which I guess are the black circles or something like that.
Oh, black hollow circles.
Yeah, maybe they were originally zeros or something, but they're zero divisors. And
and that actually makes sense. Yep.
Yes, and right, and there are all sorts of other things that make sense or should make sense to us if we really understand the picture, like how there's this short exact sequence, with the quotient group is the multiplicative group for the modulus 3, as opposed to 3 squared, which is 9. And then the subgroup is this additive group, which, again, in the picture, you can see it as this displaced version of the zero divisors, right? There's that little 3 by 3 square of blue dots.
John?
Okay, we're back.
Okay, so we had that pause there, which theoretically, hopefully, actually gave me time to figure out what I'm supposed to be saying here. So I've been saying that there's this puzzle that I'm trying to address here. So the puzzle is this. We're trying to understand the Artin reciprocity theorem in a visually intuitive way. And we've got a Galois correspondence of sorts here between subfields and subgroups. And I suddenly noticed last week or whenever, I suddenly noticed that I have more subgroups than I know what to do with, which means that correspondingly, there must be corresponding subfields to correspond to these extra subgroups that I don't know what to do with. And the puzzle that's been puzzling me is basically that, what are these mysterious extra subfields that I wasn't expecting to have? And let me just also mention a slightly different viewpoint on some of the things that we've been talking about here. So I'm talking about subfields here. I just want to say something about the idea of subfields here, trying to classify subfields of like the algebraic numbers and trying to classify them, and why we're interested in that, just sort of from a general viewpoint. And the viewpoint I want to emphasize here is that, classification of subfields is possibly, in some ways, an unnecessarily highbrow way of thinking about things. That arguably a more concrete lowbrow way of thinking about this is that what we're trying to do is like we're trying to classify irrationality. We're trying to classify irrational numbers, right? There's like, I don't know, there's maybe like a hierarchy of levels of irrationality. There are some very simple kinds of irrationalities like square roots. And then there are more complicated ones. And you can imagine, you know, a big mathematical project that people may have been working on for centuries to sort of bring some order into the classification of irrational numbers. But the way that history plays out, perhaps, is that, you know, it gets put into different words, that people are trying to understand these subfields of the algebraic numbers as compared to understanding the algebraic numbers themselves. But the straightforward correspondence, sort of straightforward, is that, you know, the algebraic numbers generate subfields. But of course, a lot of algebraic numbers generate the same subfield. So
you can think of those as equivalence classes, even though
exactly.
don't
There's
usually
some very
emphasize that these days.
Yes. So there's some very coarse equivalence relation on algebraic numbers that's given by, you know, generating the same subfield. And you know, so this is just a viewpoint that I find helpful to remind myself of, you know, some of the lowbrow ways of thinking about what's going on here. That when we're classifying subfields, what we're really doing is classifying the algebraic numbers in some very coarse way. And yeah, so I've been talking about this puzzle that I've been trying to work out here, and it involves, you know, finding mysterious, unexpected subfields. But from the lowbrow viewpoint, it's like just mysterious extra irrational numbers, mysterious extra algebraic numbers that I wasn't quite expecting. And at the moment, we're not being very ambitious. We're not looking for, you know, really understanding the most peculiar algebraic numbers in the world. We're trying to understand some of the simplest algebraic numbers in the world. And all the ones that we're trying to understand are cube roots of certain kind of, certain very simple kinds of numbers. Maybe the modifier I'm looking there is that we're looking for these very abelian cube roots. There's a certain condition that causes these cube roots to have an abelian Gaussian group or something like that. So yeah, so we've got a picture on the screen, which again is showing us, I mean, the picture is kind of messy, but you can still get the idea that we're trying to draw subgroups of this Gaussian group. But now I'm going to switch to a different picture here. Now I'm going to switch to some, maybe this will be the only time that I have to do this switching back and forth. So I'm switching to some pictures of some mathematical programs that I've been fooling around with. So is this showing up correctly now?
Yep.
So yeah. So let me tell you what this, well, actually, let me ask you what this is a picture of. You know what this is a picture of?
Oh, I can read. It says Gaussian congruence. So they're presumably.
Yeah. Well, right. That's not too much of a giveaway, right? Because just the fact that it's a square grid, that already tells you that it's some sort of.
Well, but I'm hoping that these are numbers that are congruent to something.
Okay, but I think you're trying to be too clever, because that's not exactly. This is something more basic, I think. Well, I don't know. This is really something more basic. You don't have a stupid guess about what this is a picture of? I hope it's the right picture.
I could random stupid guess, but it doesn't look right. I mean, one thing I've sometimes seen is like picture of the Gaussian primes.
That's what this is.
Okay.
If I didn't screw up, let's hope, again, look, every time I show you a picture, let's hope I didn't screw it up too badly. And yeah, and
one thing about that, by the way, is just that giving something fourfold symmetry automatically, or actually maybe eightfold symmetry, automatically makes it look much more organized than it otherwise would. So
yes,
there have been
yes.
times at which I thought, wow, the Gaussian primes are much more systematic than the ordinary primes. But then I thought, well, yeah, anything looks systematic.
That's an important point, but I still have the feeling that, despite the fact that they're sort of cheating on us in that way, that, somehow if you could just think as good as you could see, you could really learn something from this picture. Just from staring at this picture, you could really learn something about the Gaussian integers. About everything. Learn something about, Galois theory and everything. But I don't know. Again, right. Maybe I'm tricking myself. Just the 8-fold dihedral symmetry is.
Yeah, I mean, there seem to be like diagonal lines.
Yes, yes, exactly. You're right. Our visual system picks out these lines, and somehow our visual system is, interacting with patterns that exist in the Gaussian integers. So it's not just completely a trick. There's something going on here. There's all sorts of things going on here that, some people may know a whole lot about, but that's a complete digression at the moment. I just like staring at these pictures just because there's something to learn from them, but that's not what I'm going to try to learn today. So this is just a picture of the Gaussian primes, but we have some other pictures here. Let's see if we can find the right pictures.
Oh, wow. That's weird.
So some of these pictures are a little bit mysterious. I don't understand why the third quadrant is missing there. This is supposed to be a picture of some primes that satisfy a congruence pattern, but I'm totally confused why how did the third quadrant manage to not be there. But also, right, I mean, I'm not sure my human visual system is good at picking out the pattern here, right? I mean,
there is a symmetry within the 3 remaining quarters, at least in some places.
Yeah, it could be just some stupid glitch, but what am I trying to say? Yeah, now you're making me think it's not really the third quadrant that's missing. It's like some bigger region that's missing.
Yeah.
Anyway, that right. I mean, it's right. It's kind of funny the way these splitting congruence patterns work, which is that right. It's a funny mixture of chaos and pattern. Because it's the randomness of the primes, in this case the randomness of the Gaussian primes, interacting with these very regular congruence patterns. And it's like, right, it's only in some limiting case where that there's an infinite number of primes and they have a certain density or something like that. It's only in that limiting case that that you can, that this picture contains a whole bunch of regular pattern information in it. I guess what I'm saying is that, right, I mean, it's like what you really want to do is you want to like Fourier analyze this picture, or subject it to like a band pass filter or something like that, so you're only seeing certain frequencies so that you can really see. So this is sort of a bad picture, but if we, there should be another picture in here where I've put it through the appropriate band pass filter, really just isolating one frequency.
So what's
Actually,
this?
what?
So what's this?
I guess this has gotten it's the same data as this more messy thing over here. But in some discrete sense, we have isolated a couple of frequencies here. And again, I'm using frequency in some loose sense. What they really are is just moduluses in the Gaussian, moduluses for congruences in the Gaussian integers. And the two moduluses that we're interested in here are the modulus 9. And you might remember, right? That was what we were talking about last time.
Mm-hmm.
We were talking about the Gaussian integers modulo 9 and patterns related to that. So there is a frequency of 9 here that has not been removed from the picture. But the other frequency that hasn't been removed from the picture is 2 plus 3i, which is a prime. Right, so 2 plus 3i is a Gaussian prime. If I didn't screw up, 2 plus 3i is a Gaussian prime. And it's a rather small one. And the norm of this Gaussian prime is 13. And that's helpful for what I'm trying to understand, because it's congruent to 1 modulo 12, which in particular means that there's some interesting, that there is an index 3 subgroup of the multiplicative group for the field that you get by taking the Gaussian integers modulo this prime 2 plus 3i. So I guess what we're saying here is that, I have another picture here, sort of this one's a little bit hard to see, but it's just kind of the background. Can you see that little, how visible is that? You can see it's just like the background of this picture here. And it's just, what is it?
Yeah, it's a sort of square rotated.
It's okay. What it is, this is the way that Mathematica depicts the quotient ring, Gaussian integers modulo 9 times that prime, 9 times 2 plus 3i. So in other words, let's see, 9. Okay, so it's 9. Let's see. So
27i.
You're trying to figure out how many dots are in the picture? That's what I'm trying to figure out.
No.
Oh, so what were you saying?
Never mind. I was just multiplying 9 and 2 plus 3i.
Oh, well, but it sounds like you said something about 27, which is probably
27i.
Okay, well, but that number 27, that just caught my ear when you said it, and that is important here because that's the cardinality of a 3-dimensional vector space over the 3-element field, and it just happens we do happen to. The 2 different 3s there are just coincidence, I think. Well, who knows? But let's see. So. Right? If you're going to depict a quotient ring, then, a quotient ring is sort of like a rolled up thing, but we don't have a torus-shaped screen. So we have to, introduce cuts or something. And Mathematica introduces its cuts in this way. And, maybe it has some very sensible, maybe Mathematica has its own sensible reasons for introducing the cuts in this way, but I'm not really sure. But I was commenting on the fact that I think there are 81 times 13 dots in this picture. 81 because the norm of the Gaussian integer 9 is 81. Again, norm in this funny sense. I think that's right, yeah. And the norm of the Gaussian integer 2 plus 3i, the Gaussian prime 2 plus 3i, the norm of that is 13. So it should be 13 times 81. So I think that there's 13 times 81 dots in this picture. And but they're basically the elements of the quotient ring. And then, you know, then we look at subsets of this. Why are these dots so much bigger and more pleasant than those ones? I don't know. Maybe Mathematica made the choice, or maybe I accidentally made the choice. So this is an example of a subgroup in this. A subgroup of the multiplicative group of this quotient ring. And this particular subgroup is, I think, you know, density 1/6 in the multiplicative group. And that's a lot of the subgroups that we're going to be looking at are going to be density 1/6. And we have this interplay between the subgroups of density 1/6 and the subgroups of density 1/3. And that factor of 2 there is related to the fact that, you know, there's this Eisenstein field, which is not a cubic field, but it's a quadratic field. But it sort of controls all of the abelian cubic fields. So, you know, on good days, I may remember how this interplay between the index 3 subgroups and the index 6 subgroups works. But a lot of the pictures that we're going to be seeing here are the index, the density 1/6, density 1/6 pictures depicting subgroups of index 6.
Is it true that negative I is in that picture, but a positive I is not?
Yeah, there are little glitches in this picture. Oh, why would that particular glitch happen? Right. So, okay, let's mention a couple of reasons that glitches can appear here. So one reason glitches might appear here is because of ramification. Another reason glitches might appear in the picture is something I'll completely blame on Mathematica, which is that Mathematica thinks it's being so clever, and like it tries to decide whether you're talking about integers or talking about Gaussian integers. And it treats them differently when it should really do things much more systematically. And there are some times when the picture gets screwed up because Mathematica is unpredictably deciding to interpret what I said as about the integers instead of it was about the Gaussian integers. So those glitches mean that sometimes things on the real axis, I think, get screwed up. But you've just picked out a glitch. So there's that missing I right there. And I think that must be, I think there should be an I there. And why did that glitch happen? I don't think it's caused by any of the glitches that I already mentioned. I think it's caused by the fact that, you know, back in this picture, remember, we started with this picture and then we just kind of subjected it to this bandpass filter. And I think what happened is that the original data wasn't expansive enough, right? I mean, if I only picked a very limited set of primes because I was just, you know, kind of using the method of, you know, just relying on the, I was just sort of using the, I don't know, the pseudo randomness of the primes or something like that. If I had, you know, if I'd used the picture.
But what is this picture supposed to be? This one right
supposed
here?
to be the Gaussian primes that satisfy the particular congruence pattern.
Okay. But that seems, yeah, okay. But anyway, it's like really weird that 1/4 of them in a big quadrant are not satisfying that congruence relation. That sounds
Yes,
false.
I thought I already admitted that that's
Yeah.
probably completely my fault, and that I have no
Okay.
explanation for it.
Not trying to blame you.
But,
I just,
but I think
yeah.
I think that you did. I like the fact that you convinced me that the third quadrant is not really that important, that it really probably should just be a duplicate of the other quadrants.
Yeah, I was noticing in the more recent picture, further down, that you were just showing me, that that picture has, except for the glitch and maybe some other glitches, it has rotational fourfold symmetry, but not dihedral eightfold symmetry. That probably makes sense if I thought about it enough.
Oh well, look, it actually this one has rotational symmetry.
Yeah, that's what I just said.
Oh, I'm sorry. Maybe I thought you said that does have deep dihedral symmetry, but no, but this one does.
No,
have
you can see that it
chirality.
really has just rotational symmetry, because like various patterns, like a little bit further out from those I's and ones, there's like these little gadgets with 7 points that are just like 4 rotated versions of them. So
Yes. By the way, I just noticed that I actually been showing the wrong picture. I mean, there are a whole bunch of pictures here. So this one, right? This one does not have the dihedral symmetry. This one only has the rotational symmetry. I actually meant to show one of the ones that has the dihedral symmetry. Let me switch to that one right now. And there it is. So that one.
Sorry, no, I don't see that one. I still see the same thing that you were showing me.
Are you sure?
Oh, no. Well, as soon as you said, "Are you sure?" it popped into view. Okay.
Oh, then it did. Okay. And now when I say that this has dihedral symmetry, I mean, right? I mean,
yeah.
If you continue this pattern indefinitely, again, Mathematica has sort of cut it off in a chiral way, but
yeah, again, modulo glitches that I can see.
Modulo glitches. Yes, modulo that same glitch again or something like that.
Yeah, and then like another little glitch that like at 3i.
Yes.
You get like 3i. You should have 3i plus or minus 1, at least if it's supposed to be like the other rectangles like that. But 3i minus 1 is also, looks like it's missing. So anyway.
But yeah, I thought you were pointing out to me a slightly more interesting glitch, which is why is 3i colored? Let's see, is that?
So what is this supposed to be? This is some other congruence?
This is the congruence relation for, right. So this one is actually just modulo 9. So you can see that's why this one looks so regular, because we're depicting it with a larger modulus than we need, which means that you can see these repeating units in it. And I think of these repeating units as like octagons, and then there are little crosses between the octagons or something like that. But this is the congruence pattern for. This is the congruence pattern for the 9th root of unity. In other words, but more specifically, for the cube root of the primitive cube root of unity. Right, the cube root of the primitive cube root of unity is the 9th root, or the primitive 9th root of unity. So this is
saying this is the. What do you mean by that? That these are the.
These are the primes.
Lit when you throw in that.
Yeah. These are the primes where over the corresponding finite fields, there does exist this primitive 9th root of unity. Except I'm not sure I said that quite right, because they exist only formally in the sense that the coefficients of these cube roots, the Gaussian integer coefficients of these mixed Eisenstein and Gaussian cube roots of these special Gaussian integers. Well, of the so let's see. So right, we've got, okay, so 1 to the 1/3. Right, that's actually an Eisenstein integer, but we're sort of treating it as an honorary Gaussian integer, which means that well, it really just means that we're mixing right. I mean, there's low-brow ways and high-brow ways of thinking of it. High-brow ways involve categorified exponentiation, but the low-brow ways of thinking is that we're just dealing with mixed Gaussian and Eisenstein integers. We're really right. We're really trying to take cube roots of Gaussian integers, abelian cube roots of Gaussian integers, is what we're studying. But because it involves, so Gaussian integers are in the game from the beginning, but because we're studying cube roots, we're mixing the Eisenstein integers with the Gaussian integers. And so this is the splitting pattern for the over the Gaussian integers. This is the Gaussian congruence pattern for the splitting pattern for the cube root of 1 to the 1/3.
So these are the Gaussian primes that split over 1 to the 1/9.
Yes, over this abelian cubic extension of the mixed Gaussian and Eisenstein. Right. I guess we should say over the Gaussian, right? So this is right. I mean, right. I mean, this is this thing about the interplay between the 1/6 and 1/3 thing. So we're right. We're really dealing with abelian cubic extensions. How does this work? We're dealing with abelian cubic extensions of the Gaussian field, but as an auxiliary device, we look at these abelian 6th degree extensions that include the Eisenstein integers, and so so this is a splitting pattern for the 6th degree extension. That includes, right. So actually, right, this is coming from, starting with the Gaussian integers and then adjoining all the ninth roots of unity, all the primitive ninth roots of unity, which that also causes the primitive third roots of unity to show up. When you put in the primitive ninth roots of unity, the primitive third ones show up. So it's, so that's what this is. And
it's drawn in
I was commenting on
humorously fallible way.
Say it again.
And it's drawn in a humorously fallible way.
Yes. That's right. Humorously glitchy way. That's what you mean, right?
Yeah.
But I was commenting on this dot right here and this dot right here. I think those are glitches. And I thought you were mentioning those glitches, but I think you were mentioning the glitch next to this one here, right here, the missing thing here. But this is a unwanted visitor. Well, it's not an unwanted visitor, but it has to do with ramification, I think. So it's right. There's some glitches here that we blame on Mathematica, but this is a glitch that we actually blame on mathematics.
Mathematics. Yeah.
And there were also glitches that we blame on me.
Okay. I can.
I think these are ramification glitches because, right, there's 3 dots in a row right here, and there should be 3 dots in a row right here, but I don't see 3 dots in a row anywhere else in the picture. So I think those are ramification glitches. So yeah, so okay, so let's think about what's going on here. So we've got, like I say, what is it? 81 times 13. Let's see, the 81 thing. What is that like? What am I trying to say here? I'm trying to convince us that there is. Well, first of all, let me show you how many pictures I have here. So I have 1, 2. Well, let's see. I have 13 of them. I have 13 pictures, 13 pictures if I can find them here. And 13 is the size of the projective plane over the 3-element field. And right, the projective plane over 3-element field comes from a 3-dimensional vector space over the 3-element field. So I guess what I'm trying to say is, what am I trying to say?
So that 13 is not coincidentally the norm of 2 right?
Oh, sorry, you're asking me at gunpoint whether that is a coincidence or not?
Yes.
I think that's a coincidence. I think that's
really?
a coincidence. You
Wow.
were guessing it wasn't a coincidence?
Right. I was guessing that. Yep. But I guess it's very weird to get a projective plane to be in correspondence to.
Yeah, but this vaguely reminds me of some other weird coincidence that you pointed out one time, right? We were looking at the 20th cyclotomic field, and the Galois group had 8 elements, and it also had 8 subgroups. And this seems like a very analogous random coincidence, but maybe they're not really coincidences. I don't know. So I mean, what we have 13. Right, we have 13 index 3 subgroups because that's the projective plane of a 3-dimensional vector space over the 3-element field.
Yeah.
But
For
that's just
for readers not in the know. That's because 1 + 3 + 3 squared is 13. That's how you count the size of the projective plane over any field you do.
Yes, but another good way to think about it is we've got 27 elements in our 3-dimensional vector space.
Mm-hmm.
We remove the 0 vector. So there's only 26 non-zero things. And then we just divide by the cardinality of the multiplicative group. Yeah. So it's 26 divided by 2, which is 13. And that agrees, for some sensible reason, with the other calculation that it's 1 + 3 + 9. Yep. And so, right. So there's 13 is showing up for some in apparently 2 different ways. We just said one way that it's showing up as the size of this projective plane. The other way is that it just that happens to be the norm of this prime 2 + 3i. And I think that's just a coincidence, but who knows? So let's see. So I've got, I mean, let's see. So I've got 1, 2, 3, 4, 5, 6, 7. Oh, well, those all look the same, but I'm actually going through 13 different programs here. So yeah, okay, right. Let me see if I can get them all to show up here. So this is the second one. This is the mysterious one. Right. This is the one that's the answer to the puzzle, kind of, or maybe that is the puzzle. This is the one we already looked at. That's chiral. This one, I think this is the one that actually turns out to be the same as the previous one, except the opposite chirality.
Cool.
And this one, so those four, let's just go through those four again, because these are the four that don't actually involve the prime 2 plus 3i. So they only involve the prime 9. So these four here all have that visual thing to them that you can sort of see the period 9. You can see the repetition of the units, the repetition of these little sub-pictures, and the sub-pictures are these little 9 by 9 things. So those four of them, including the two chiral opposites.
So there are,
Yeah.
what is it? There are 4 congruence classes in the Gaussian's mod 9, 4 invertible.
Is that what it is? I was going to say that it is a 2-dimensional vector space. Yes, you're right. I mean, so yes, it's again, you know, we had 27 minus 1 divided by 2 is 13, but this is a 2-dimensional vector space, so it's just 9 minus 1 is 8 divided by 2 is 5. So this is just the projective line. This is just the projective line over 3-element field. So when we use your method, it's just 1 plus 3. And the 1 is the point at infinity, and the 3 is the affine line. And back when it was 13, which was 1 plus 3 plus 9, I guess the 1 plus 3 was the line at infinity, and the 9 was the affine plane. Did I say that right? Affine projective plane? Yeah, right. When it was the projective plane, 1 plus 3 plus 9. The 1 plus 3 is the projective line at infinity. Is the affine plane. Okay. So right. So those four are the ones on this projective line. So yeah, I don't know. Maybe we should think of this as the line at infinity in this projective plane of 13 different pictures. But so, right, the other ones are the ones that really use the full modulus of 9 times 2 plus 3i. So let's see if we can see what those look like. Right, those should not have this obvious periodicity. I almost thought that does have periodicity. Which one is this? Well, right. I have figured out a lot of the puzzle. There's still some things puzzling me. See, I think there is one that we're still searching for here that should have some hidden periodicity, but not period 9 in it. But okay, that's one of them. I'm just trying to bring all of them up here. This is another one. I don't know. What does your visual system say? Does it say that these are random aside from the dihedral symmetry, or?
These just have rotational symmetry, not dihedral symmetry, but.
Oh, right.
But
is that right? I guess you're right that.
I mean,
right, because 2 plus 3i is sort of chiral because it has this conjugate 2 minus 3i. That's not the same, and that's making all of these chiral, except for the 2 special ones that didn't involve 2 plus 3i at all. So there's this one, okay. But again, just my naive, stupid question is your visual system telling you anything about this, or it just looks like random data that's been rotationally duplicated?
Yeah, it looks
sort
of random. Yeah, apart from that, yeah.
And then there's this one.
And the usual glitches.
Yes, all the usual glitches. Oh, let me just fix this one. Well, this one was this one I showed it at a different
resolution.
I subjected this one to the wrong bandpass filter. Let's ignore this one for a second. Because I was searching for the one that, you know, had some hidden period, allegedly has some hidden periodicity, and I thought that might be it, but I don't think it's the right one. So it's like that's just a, oh, I also glitched that one. Okay. Let me get some of these here. Okay, back to normal. And this one here. Right, okay, so now it does kind of have the feeling we're just kind of staring at random data here, but these are 13 different subgroups. And there's a reason why they have these, you know, why there's 13. It's this projective plane. But also, let's just remind ourselves, there's this 13 element projective plane, but it came from a 27 element vector space. And if we had been doing things in a more morally correct way, we might have actually had 27 different pictures, because instead of studying the splitting patterns of these abelian cubic field extensions, we would be studying the Frobenius patterns of torsors. And, you know, when you do that, you actually see the vector space rather than the associated projective space. So, you know, it's, again, my fault for some kind of coarseness here, that we're cutting corners. We're only seeing the projective spaces, the projective space instead of the vector space. All right, another one here. Right. At this point, it's mostly feels like staring at random data, but it's actually not random at all. It's this one, and then there's, oh, and then maybe this is the last one. Yeah, this is the last one. So there's 13 of these here. And all right, so now let's try to actually give some alleged answer to the puzzle. So I guess the puzzle really goes back to the original four that have this, right? Because the puzzle doesn't really involve this extra 2 plus 3i. Okay, yeah, maybe that's a good point. Maybe we should have really been concentrating on ones that don't involve 2 plus 3i at all. So there's this one, this one, this one, and this one. So there's this one, which is supposed to be completely non-mysterious. This is the one, right? This is the one that's actually just using this norm pattern. So this is showing that the primes where the norm of the prime is congruent to 1 modulo 9. And that pattern, you know, makes very good conceptual sense in terms of being the pattern for the 9th cyclotomic field, or the 9th cyclotomic extension of the Gaussian field. So this is the very unmysterious one.
I see 3 plus I there, which does have norm 1, 9 plus 1.
Yes.
Yeah, so that's good.
Yes. So this is the very non-mysterious one. Then there's the chiral pair. And somehow the fact that they're a chiral pair means that, you know, they can't be very important. I mean,
sorry, that's a chiral pair of that other one?
This one and this.
Doesn't look like it. Really? Oh, okay. Yeah. Okay, yeah.
Again, if you know, you have to deal with the glitches.
yeah, not.
Boy, do I really, how many of these glitches do I really understand?
Sorry, I was looking at one that had 3 plus I in it, which isn't either of these two.
That's right. No, I'm saying, remember, there are 4 of them here. I'm
Right,
counting on the fact that we've got 4 of them. We've got this original one.
Okay.
A very non-mysterious one. We've got this one, which is the very mysterious one. And then we've got the two chiral ones, which are just, you see what I'm saying? We've got a projective line, 4 points, 3 points plus a point in infinity. And so on this projective line, we have two special points coming from the two basis elements of the two-dimensional vector space that corresponds to this projective line. And so there's the mysterious one and the non-mysterious one, the mysterious basis element and the non-mysterious basis element. So this is the non-mysterious basis element. This is the mysterious basis element. And these two are the chiral pair that are just sort of like, and the rest. Like on Gilligan's Island, they say, and the rest. These are the ones that are too unimportant to even bother thinking about in detail because of the fact that they're a chiral pair. They can't have too much individuality if they're just a chiral pair. So the mysterious question is, what is this one? And okay, so let's rehash some of our naive guesses, because I think you and I were both guessing, making some very similar guesses for what the answer to this puzzle could be. So we had something like the non-mysterious one was just had to do with the cube root of the primitive cube root of unity. And it really didn't, it barely even involved the Gaussian integers. It was really just a congruence pattern from the ordinary integers, but then borrowed over into the Gaussian world by this norm rule. So for the mysterious one, we were kind of guessing that it would be something similar to the non-mysterious one, but just somehow adapted to the Gaussian integers. So like I was thinking of silly things like, maybe the cube root of I or something like that. But that doesn't work because the cube root of I is already there. It's already in the field. It's not an extra thing to be joined. The cube root of I is, am I saying this right? Negative I. Yeah. So that was one of my naive, stupid guesses that didn't seem to help at all. So I don't know. Do you want to take any stupid guesses, or I just should sort of tell you what the answer is?
You should tell me what the answer is. I'm pretty confused.
Right. So what it is it's basically the cube root of, it corresponds to the cube root of 1 plus 2 times I plus 2 times W, where W is just this name that I'm using for our favorite primitive cube root of unity. So it's like 1 to the 1/3, whereas I is just the usual 1 to the 1/4. So there's this number B that is this mysterious number. So W is the unmysterious number, which is 1 to the 1/3. B is this mysterious one. I hope I said that right. W is the unmysterious one, 1 to the 1/3. B is 1 plus 2 times I plus 2 times W. And so where does this come from? All right, so let me try, okay. So let me try to state a conjecture here. It probably is just a theorem, but let me see if I can state this. So it's like, what are we trying to do here? We're trying to understand all the abelian cubic extensions of the Gaussian field. And the idea is, okay, and now I really have to write this down somewhere. So I'm gonna have to switch to my notebook here. So let me try this smoothly as I can. I'm pretty good at it. Okay, so that's visible now, right?
Yep.
And so what am I trying to say here? That let's take GL1 of the Gaussian rationals. That's supposed to be a little notation for the Gaussian rationals.
Mm-hmm.
So that's a field. Let's tensor it with the 3-element field. So it becomes a vector space. I guess I should modify this slightly here. Let me say, I forgot to incorporate the Eisenstein. We're sort of mixing together the Gaussian and the Eisenstein here. Let me see if I can write it more correctly. So we're going to take the Gaussian rationals combined with the Eisenstein rationals. Okay. And then we're going to tensor with the 3-element field. So now we have produced an infinite dimensional vector space over the 3-element vector field. And then I think we want to take this thing and mod out by the action of Eisenstein conjugation. Actually, I guess it's twisted Eisenstein conjugation. That means there's a factor of 1 in there. Right? This is this
Factor of 1.
Factor of -1.
Uh-huh.
Am I saying that right? I think it's the things that are. Yeah, right. Right. There's a certain eigenspace that I'm taking here. Eisenstein conjugation is acting as a reflection operator on this infinite dimensional vector space over the 3-element field. And so it's got, 2 different eigenspaces. And we want the non-trivial one, the anti-fixed points. So this is sort of our conjecture for what should be the classification of the Z mod 3 torsors over the Gaussian field. And I mean, this is a reasonable conjecture, and it's kind of saying, if you think about what this is saying, it's kind of saying things about splitting patterns. Well, when we express it this way, again, we're talking about the torsors, which is slightly different from the abelian cubic extensions. So this is like the rule. This is the set. The elements of this thing would be the. Right. This is an eigenspace. So this is itself is an infinite dimensional vector space over the 3-element field. And the elements of this vector space are the Frobenius patterns of the torsors, according to the conjecture. But I think it's probably true. This is probably a true conjecture. And so, in other words, we want to think about. Well, okay, yeah. So this is going to give us the Frobenius patterns of the torsors, and then if you want to think about the splitting patterns of the abelian cubic extensions, then it's almost the same thing, but it's just right. It's just kind of like right. It's just a projective picture of that infinite dimensional vector space. Am I saying that right? Yeah, I think that's right. So we want to intuitively understand what this infinite dimensional vector space is like. That's how we're going to understand our classification of the abelian cubic extensions, or the more or less equivalently the Z mod 3 torsors.
Mhm.
So, you have to try to use your understanding to, analyze this. And if you think about how this works, we're getting something, this vector space that we're getting is very close to having a basis that's indexed by the Gaussian primes. Right? Does that make sense? Let's see. So
The word
say that again.
the word 3 should in there too.
What did you say? The word 3?
The
What?
word 3. Let's see. So you think that's really true? Where did the F3 go?
What do you mean? Where did it go?
So your answer, so each Gaussian prime gives an element gives a basis vector. Yeah, maybe you're right. Sorry, I just didn't see how F3 got in this thing here, went away when you said.
Well, the F3 is getting in here because if you remember our earlier discussions, we talked about the idea of, when people classify quadratic fields, they often talk about square-free discriminants or something like that, which led to you and me joking about cube-free discriminants. And that's kind of what this tensoring with F3 is doing here. It's kind of saying that, right, we're trying to classify equivalent cubes. So, right, we count 2 cubes as equivalent.
Mm-hmm.
Maybe I shouldn't call them cubes. I guess, right? We're really modding out by cubes. We're right. We're right. I maybe didn't say that right. Maybe I said we're trying to classify equivalent cube roots, or equivalent nice cube roots. These abelian cube roots, and 2 cube roots are considered equivalent. There must be a better way to say it than what I'm saying. But you know what I'm saying? Like, I mean, what am I trying to say? The cube root of 2 is equivalent to the cube root of like 16. Right? When we're classifying these cube roots, we don't consider the cube root of 2 and the cube root of 16 as different because they differ by this factor of 8, which is already a cube. Right? You don't need to adjoin the cube root of 8. So when you're adjoining cube roots, adjoining the cube root of 2 is no better or no worse than adjoining the cube root of 16, at least in the version of the game that we're playing. So
mod out by Eisenstein conjugation, you're getting this vector space of these Gaussian tensor Eisenstein.
Yeah, I mean, remember the mistake I made at the beginning was first I said this thing, and this thing really looks like it has a basis corresponding to the Gaussian primes, except maybe one tiny glitch or something like that. But this is supposed to be a sort of like twisted version of that. And if I did it right, then in this twisted version, the Eisenstein thing is like, something you give, but then you take it away. Let's hope that I did that right. But yeah, I think that's right. I think that's right. We'll have to investigate this as we understand it better. But I'm trying to give a very hand-wavy plausibility argument for why we're getting something like the Gaussian primes here, okay?
Mhm.
But there's a glitch here that's very noticeable once you notice it. The glitch is this, that look at this field, but look at the ring of algebraic integers inside it. So this is the mixed Gaussian and Eisenstein integers, which you can also think of as the 12th cyclotomic field, you know, the field generated by the primitive 12th roots of unity. And so that's got a ring, that's a ring. Well, it's a field, but it's got this ring of algebraic integers inside it. And in that ring of algebraic integers, well, it has a multiplicative group. And right, so I think I made I fell into a trap. I was thinking about the 12th cyclotomic integers. And I fell into the naive trap of thinking that the multiplicative group of that ring was just the 12th roots of unity. You ever fallen into that trap?
Probably falling into it right now
Yes.
because I'm not.
Can you think right? Right. I'm pressing you now. Can you think of any?
Can I fall out of it?
Yes. Can you think of any? Can you think of any invertible? Can you think of any one of these 12th cyclotomic integers that has a reciprocal that's not just a 12th root of unity? And I don't think it should be at all obvious. So you're allowed to give up.
Good. Well, that's good.
So let's think about this. So we've got the how do I draw this? We've got the prime 2, which is appearing with multiplicity 2, the prime 3, right? 12 is equal to 2 squared times 3. So when we're looking at the 12th cyclotomic integers, we have, like, let's see, that's the stuff relatively prime to 4 is 1 and 3. The stuff relatively prime to 3 is 1 and 2. And with the Chinese remainder theorem, this is all stuff that's mod 12. So this is like 1. Am I doing this right? Is this 1, 5? Where are 7 and 11 here? Let's see. 5 is 1 mod 4 and 5 is 2 mod 3. What about 7? Where does 7 go? 7 is 3 mod 4 and it's 1 mod 3. So maybe it's like this. Okay. So that means that the Galois correspondence that we're dealing with here. So I'm looking at subfields of the 12th cyclotomic field here. So we have the small subgroup at the top. Then we have 3 intermediate subfields. And we have the big subgroup at the bottom. This is and so this is just the rational field. This is the 12th cyclotomic integers, which is just the Gaussian combined with the Eisenstein. I hope I'm doing that the right way. And maybe I should put these in here. And so which one of these is the Gaussian? The Gaussian should be the one that only depends on 2. Let's see. How does this work? Maybe this is the Gaussian one here. And is this the Eisenstein one, or did I get it backwards?
I thought the Gaussian one whether there's a dot or not should only depend on the horizontal coordinate. Sorry, only depend on the 2 where you are.
Right. So the splitting pattern for the Gaussian should just be, 1 versus 3 mod 4.
So it seems
and that
like
would
it's
mean that the
backwards.
cosets. Okay, so you think I got it backwards? That's what you're telling me, right?
I think, yeah. Tentatively, but that seems to be what you just.
It's probably not even fatal if I get it backwards, because the actual focus of interest here is this mysterious one in the middle. So do you know what that one is?
Something like.
I mean, this is Q adjoin 1 to the 1. Well, it's Q adjoin 1 to the 1/4, but it's also just the Q adjoin the square root of -1. And the Eisenstein thing is, Q adjoin the 1 to the 1/3, but you can also just think of it as Q adjoin the square root of -3. So does that suggest what the one in the middle?
Yeah, okay. That way of describing it makes me want to stick in Q adjoin square root of 3 is the.
That's what this is. That's what this is.
Middle guy. Yeah.
That is Q adjoin the square root of 3. And if you think about the things that have reciprocals in there, in that ring of algebraic integers, that is much more suggestive. So what is the thing? It's like, what are we trying to say? It's like, what am I trying to say? 2 plus radical 3 times 2 minus radical 3.
It's 1, so they're invertible.
Is equal to 1, yeah.
Okay.
And right, and this is not finite order. So this is like an infinite order thing in here. And you see what I'm saying? That is contributing to this. This is giving us like an extra generator in this vector space, an extra basis element in this vector space, or something like that. So that's this alleged solution of this puzzle, that this is the extra thing. In other words, there's a cube root associated with this thing. I'm tempted to call this an extra prime. I'm not sure if that really makes sense, but again, it reminds me of what Conway thinks of -1 as an extra prime. Except, wait a minute, does that? But -1 isn't infinite order. But it's like an extra thing in the multiplicative group, and Conway calls -1 a prime, just like 2 and 3 are prime. Just what it is. I'm not sure if I'm doing anything analogous to what Conway is doing, but
well, you are. I mean, it is true that.
Yeah.
seems like it's true. You're saying that like both units and primes give basis vectors for this type of
Yes, I'm
vector
saying
space.
something like this. Yes, and right. So I mean, so sorry. I hope that was okay. Yes. So okay, what did you just say again? I guess got distracted. So the
Thinking that like both units and primes contribute extra basis vectors when you take GL1 of some number field, and then you
that's right.
tensor it with a finite field to get a vector space.
Yes. Yes. Yes.
That was a little sloppily stated, but that's the idea, I think.
Yes. Yes. Sorry, I just got distracted by this thing here, and now I'm struggling to remember what I was just about to say. Right, the alleged explanation for the puzzle is that there is this extra thing corresponding to this quasi prime or something, which is really not a prime, but it's like a it's like a dimension, an extra dimension in the multiplicative group, or in the multiplicative group when you turn it into a vector space over the 3-element field. And so it seems like what we're saying is that when we look at this multiplicative group, GL1 modulo the Gaussian integers modulo 9, and when we notice that it has more index 3 subgroups than I was expecting. I was only expecting one, and it turned out to have 2 of them. And from what we're saying, it sounds like that is secretly telling us about some extra unit in the mixed Gaussian and Eisenstein integers. So I would like to understand that better. How it is, right? We're saying that there's a correspondence here, and in this correspondence, there is this extra thing that needs to correspond to an extra dimension of units in the multiplicative, in an extra dimension of units in the unit group. And that seems like something I would like to understand. But that would be an even deeper resolution of the puzzle. But this is my alleged resolution of the puzzle. My alleged solution of the puzzle, answer to the puzzle. That so to me, this is a somewhat satisfying solution to the puzzle. I mean, there's more things I need to understand here, but it is, it's saying that it's propaganda for the idea that this is a correct conjecture. And it's telling us about things that we should do to try to understand this. And so let me draw a little chart here. So I've got these 3 numbers that I'm calling. So I've got this number W, which is really just the primitive cube root of unity. And then I've got B, which is 1 plus 2I plus 2W. I don't know if I can do this on the spot, but this number 1 plus 2I plus 2W that I'm calling B, this is somehow related in some funny way to this thing 2 plus radical 3. Are these like maybe just differing by a unit or something, by a 12th root of unity? I'm not quite sure, but they're related in some way. So, I mean, this is the actual thing that I'm taking the cube root of, this B, So we have one extension that corresponds to taking the cube root of W. We have another extension that corresponds to taking the cube root of B. And those are actually the only ones that involve this modulo 9. But then I was really trying to understand the things involving the prime 2 plus 3I, and that, so okay, so there are corresponding primes over here. So one W equals the primitive cube root of unity, that's somehow related to the prime 3, right? So these are like cube roots, and they're corresponding to primes, except that, I'm stretching the notion of primes here somehow, because it's including these extra things that really correspond to units or something like that. So somehow the cube root of the primitive cube root of unity, that's corresponding to the prime 3, because that's the modulus of the splitting pattern. And the cube root of this number B, that's corresponding, right, that's corresponding to this mysterious extra thing that, I mean, I'm sort of blaming it on Conway. I don't know if that makes any sense to it's like a weird Conway prime, but I don't even know if that makes any sense to blame it on Conway, but it just reminds me of this idea of having some extra primes around because it has something to do with something. And this number K is going to correspond to the prime 2 plus 3I. And so, I mean, 2 plus 3I was chosen as, just sort of like, I was going to say randomly. Actually, it's not that random. I just tried to make it the easiest example I could come up with. But, it's like, it's not supposed to be special like the way these other two are. These other two are special in such a way that it produces this puzzle that I tried to solve. But for the actual corresponding number corresponding to K, it's, I was hoping I had it written down here. It's -1 plus 5I. Plus -2 minus 3I times W. And, so you take the cube root of K. And those correspond to, I mean, right, so we have these 13 different fields corresponding to these 13 different subgroups. But out of those 13, there are really 3 important ones, right? Because the 13 is really just the projective plane from a 3-dimensional vector space. And that 3-dimensional vector space has a 3-element basis. And that's what this is really, that's what these 3 things, W, B, and K, are corresponding to, this 3-element basis
Do you get all the 13 fields by taking the
Yes.
suprema of these fields in the lattice of subfields of some?
Actually, no. That's is that true? No, that's not quite right.
Oh.
Don't think of it that way. Try to think of it as we've got W and B and K, and you could take the cube root of any one of W, B, or K, but you could also take the cube root of W to any exponent times B to any exponent times K to any exponent. And those exponents really are integers, and they only really matter mod 3.
I see. Yeah.
So that gives us sort of 27 possibilities, but then it doesn't really matter. It's really just projective, unless you keep track of the orientations, and then it really is 27 or something like that. And so that's explaining these things. So, so this is how it's all sort of supposed to fit together. Now, let me just leave off with one puzzle that's, I guess, supposed to be the next puzzle. Right. I guess this is like the next puzzle, right? I mean, just one puzzle leads into the next one. And so I, sort of came up with an explanation for the last week's puzzle, but now I'm trying to state this week's puzzle. And I have the feeling that this week's puzzle is easier, or it's based on a more naive confusion than last week's puzzle. So what am I trying to say here? So let's just kind of flip through these 13 things here. Well, I suspect that one of these 13 is not going to depend on the modulus 9, but is only going to depend on the modulus 2 plus 3i. And that was sort of my goal here, really, was to find that one. And I haven't found it yet. And it's sort of, there's something screwed up here. So I have to figure out what's really going on here. But I think, what am I trying to say? That see, I mean, right, this reminds me of the way that where's my cursor, that we were just looking like at the Galois correspondence for these quadratic fields involving the square root of -1, the square root of -3, and the square root of 3. And so like everything here is periodic with period 12. You never have to get worse than 12, period 12 here, when you're understanding the splitting patterns here. But let's see, the Gaussian one is actually period 4. The Eisenstein thing is period 6. What about the square root of 3? What is that? Maybe that one really is. Yeah, I think, right, that one is actually period 12. Right, so right. So let's consider the square root of 3 and the square root of -3 as a matched pair. And the square root of -3, it corresponds to a congruence pattern where the period is 6. But I think that for square root of positive 3, I think you need to go all the way out to period 12.
Mhm.
Right, and I guess if you do it, right, I said Eisenstein is period 6, but I guess it's you can think of it as period 3, actually, I guess. So there's some funny thing going on here that like -3 is mysteriously better than 3.
Uh-huh.
And right, that's the one that has an unusually small modulus. And I was hoping that an analogous thing was going to happen in this cubic case, analogous to this quadratic case. I was hoping that. See, now I'm making this horrible mistake where I'm thinking I'm showing you both pictures at the same time and you're not seeing both pictures.
Right.
Let me just try to flip. Yeah, okay. Well, I mean, I'm trying to wrap it up here, so maybe I shouldn't flip back to the pictures, but I'm just acknowledging the fact that I've been saying stuff where I was showing you the wrong pictures.
Oh, didn't even notice. Okay.
Let's see the picture. But let me just check. The pictures that you are seeing are these ones where you see the. Which ones are you seeing now?
I'm seeing your notebook saying.
Oh,
roots
okay.
and forms.
Okay. So that's okay. I guess that's okay. But what I meant to do next. Okay, so now it's okay. Now I just have to flip back. Let's see. Okay, all right. Let me just make sure I don't need anything else in the notebook. Yeah, I think I'm done with the notebook, and now I'm trying to switch the screen smoothly as I can back to the Mathematica pictures. Right, and I meant to just flip through this, catalog of 13 things here. So we have the first one, the second one, third one, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th, 13th.
Mm-hmm.
And I'm hunting for one of these that I think should have this unusually small modulus. And it's just not visible yet. I mean, I look at them and none of them seem to not involve the modulus 9. But I think that could be because I'm just getting screwed up about the interplay between the index 3 subgroups and the index 6 subgroups. In other words, I'm trying to sort of do this Fourier analysis or bandpass filter or something like that. And maybe I have to filter out the quadratic thing so that, I don't know. I don't know. I guess this week's puzzle is not articulated very clearly, but I'm still right. I did sort of. I mean, like I say, I'm searching for ways to visually understand the Artin reciprocity theorem, and I've been, but in trying to do that. I've somehow been managing to, not very clearly state the theorem yet. But like I did, I did state that thing in terms of the 3-element field and the sorry. Just trying to sorry, I'm just trying to remember what I was talking about. I was talking about this week's puzzle. and the way it's very disorganized at this point. Right. So really, this week's puzzle is going to be for me to try to figure this out. I didn't articulate it in a way that anybody else can appreciate yet. But right. But what I'm trying, right. This puzzle, right. This puzzle is really just part of the larger puzzle of trying to not just understand how to visually appreciate the Artin reciprocity theorem, but also how to connect it to the actual written theorem. So I'm right. I mean, there's this sort of correspondence between the Z mod 3 torsions over the Gaussian field and this thing involving the general linear group of the mixed Gaussian and Eisenstein field, and then tensored with the 3-element field, and then modded out by Eisenstein conjugation. That's where I'm having something like a precise statement, a conjectured precise statement of the Artin reciprocity theorem. And I mean, that's a little fragment of it, but then you just generalize it, and that should give the whole theorem. And so this week's puzzle is really just supposed to be part of that. That I'm trying to, you know, state the theorem in a precise way that I can understand how to connect to the pictures. And I still have the feeling, even if I'm not doing it the right way yet, I still have the feeling that clarifying this isomorphism of cohomology groups, you know, the one cohomology group that involves the Z mod 3 torsions over the Gaussian field, and the other cohomology group that involves something about the homomorphisms from the multiplicative group to something, and or certain special kinds of homomorphisms. And I'm just trying to state that theorem in a precise way that will match with the pictures. And in the process of doing that, I'm searching for one of these 13 pictures that should have a smaller periodicity, but I haven't quite figured it out yet. I think because I'm like mixing two frequencies together in the wrong way, and I can't clearly see the frequency that I'm trying to focus on. I'll have to try to make that make more sense later. But I just want to say one thing before I quit. The one thing I want to say before I quit is that everything we're doing here is understanding. Almost, the main stuff that we're doing here is focus on understanding abelian extensions of the Gaussian field. But it's interesting that there's another topic in Galois theory and number theory that has the same goal, but seems to do it in a very different way. And that other topic is the Kroneker's Jugendtraum. So Kroneker's Jugendtraum is another great tool for trying to understand and classify abelian extensions of the Gaussian field. But it involves, you know, these Gaussian elliptic curves and stuff like that. So in some ways, it seems very different from what we've been talking about here. But on the other hand, there are, you know, all sorts of indications of secret relationships. So it would be a very interesting project, and that's one of my projects, is try to understand the relationships between the kinds of things that I've been doing today, which I still need to do in much better ways, but trying to understand the relationships between what I've been doing today and, on the other hand, Kroneker's Jugendtraum as applied to the Gaussian elliptic curve. So I'm sorry I've drawn on for so long, but I guess I'm sort of running out of things to say. And sorry for all the disorganization and everything, but I I hope this was okay.
Yeah,
And I
sure,
guess
it was
we'll
okay.
try to
Yeah.
continue next time, I guess.
Yeah, yeah, that sounds good.
Okay, so thanks a lot, and I'll see you, and okay, I'll see you. Bye.
Yep.
Okay.